Alright, so in this video we're going to be introducing you all to the concept of trees. So we're coming back to this slide that we have revisited quite a bit, and we're going to look at where we've been. So we've now looked at how to build abstractions using an array. Remember, an array is when you store memory. You store your data in memory, or in general, when you store your data in a block of memory that's sequentially connected, so all of the memory is next to each other. Then after that, we looked at how to build abstractions in a linked structure. This is really helpful because it's setting us up for trees. A linked structure means that the data is stored perhaps in different parts of memory or different parts of a system, and then they're linked together somehow, either with a singly linked list or doubly linked list, but it is linearly connected, meaning you have to travel through the different links in order to get anywhere in the middle. So that moves us to a tree. So a tree data structure is different than a linked list, but shares a lot of similarities in that you're separating out the data and storing it in different locations and then linking it up. But the linking is different because it's no longer linear. So instead of having one node connect to another node, which connects to another node, you have one node and it can connect to any number of nodes. However, this is one directional, so you have to go through that first node to get to however many other nodes it connects to, and then those nodes also can connect to any number of nodes each as well. And that's the basic idea of a tree, is that you're no longer linking everything in this linear way, but now you're linking it in the form of it kind of growing just like a tree does, from a trunk to a branch, to the twigs. So that's what we're going to be focusing on for the next 2 weeks. So trees are pretty natural for people to understand because we use them a lot in our everyday lives, in all sorts of different places. So here's an example of creating a tree out of all the different regions on Earth. So we have the world, which links to different countries. The US links to states, which link to cities, or the other countries just link directly to cities. You could then go to counties and neighborhoods and etc. And this type of hierarchy is kind of the nature of a tree, and a lot of things can be broken down in this way, even things you might not have thought of. But there's plenty that you have thought of. So like a family tree is an obvious one. A file system in your computer is very much a tree, right? Because it has like a root folder and then those folders and then other folders. The programs you write in your code are hierarchy oriented as well, right? So you have a main function, it calls other functions, which call other functions, but you could even break it down into variables or code blocks, or kind of the sky's the limit. So what we're going to spend time in this video doing is making sure that we understand the terminology of trees. And this is an important step that I really advise you doing before you start learning about any new concept. And to practice your terminology, one really great way of doing that is to make sure that you're having discussions with people in the class about this stuff, so that you're forced to try to recall all of the terminology. Post in our class discussions, lab, office hours, all these things. It really, really helps, and it's a really, really important part of learning new concepts. So a tree is a collection of nodes, and you can have an empty tree, but if it's not empty, then you have a root node, which is that first node that everything comes off of. And each of those nodes that come off the root node are basically subtrees. So this is a very recursive structure, and all of the nodes are connected to each other by edges. So those edges are directed, meaning that they only have a single direction that they can take, and it's always pointing down. So we don't typically draw the arrows of trees because trees are always directed, but you'll notice when we start talking about graphs later on in the semester, we're going to indicate whether those edges are directed or undirected, because both are possible. So A is the root in this tree here. A couple other things to point out. So B here, we call B the child of A. F here is the child of A as well, but it's also the parent of K, L, and M. So you can use those phrases, child and parent, which are really useful when you're talking about different algorithms or you're referring to different parts of the tree. Another really good thing to notice is that there's this kind of fence post issue with trees that's important to remember. That is that if there are n nodes in a tree, there's n minus 1 edges, and that's because the root doesn't have an edge coming down to it. All of the nodes that have no children, we call those leaves. Any node that has the same parent as another node, those two nodes are called siblings. We can define a path as the edge that connects a parent to its child, but you can have paths from any set of nodes you'd like. So the path AEJO that's an example of a path, and it has a length of 3 because it has that number of edges. But you could also have a path from EJO. That path would be length 2. And so a path is a general word as the distance between two nodes. The depth of a node is the length from the root. So the depth of the node J is 2 because it is 2 edges away from the root, which is A. The depth of the root itself is 0. The height of a node is the longest path from the node to a leaf. So the height of node F is 1 because it's 1 edge from its leaf, which is K. The height of all the leaves is 0. You can also talk about the height of the tree in general, and the height of the tree in general is just the height of the root. So it's like basically the longest path from the bottom leaves to the root. So in the case here, the height of this tree is 3. And we are going to spend a whole video on height and the algorithm for determining height of a tree. So this is just to kind of get you familiar with the initial terminology. Okay, so a couple other terms that are important. And by the way, a lot of these terms are going to carry over to graphs as well. So it's good to get familiar with them. So trees, nodes inside of trees can only have one parent, and they cannot have cycles. So this is an example of a node A that would be coming from 2 different parents, and that's never allowed. A tree can't have that feature. You can have that type of structure. That's basically a graph. It's just a tree assumes that every node only has one parent, and that's that directed nature of the tree. Here is another example where node A has 2 parents as well. Let's talk about cycles. A cycle is when there is a possibility that your tree can, you can be traveling down a tree and you can come back to a node that you already visited. Yeah, that's basically what it is. So here, S goes to T goes to N. In a tree, once you get to N, you've reached the end of the tree. But if there was a connection back to S, that would create a cycle. And so you can assume in trees that no cycles are present. That's something you cannot assume in graphs because it is possible to have cycles in graphs. Here's another example of a cycle that's slightly different. So connecting these two children of S together would also not be possible. So these sort of restrictions to the tree structure are important, but it's also important to just know the terminology. So one parent and no cycles. Trees are one of the most important data structures, and they're really, really important for efficiency in algorithms. They come up all the time because they're so efficient, because they're such an efficient way to store things. The main thing is that trees, particular types of trees, which we're going to talk about in our next video, offer us, well, actually all trees offer us log n operations where, you know, the base is different for what kind of tree it is. And log n operations are great. And if you just want some like numbers to kind of process how efficient they are, at Amazon, let's say that there's 350 million products. Because of the log n operations, if you just take that n, 350 million, and you take the log base 2 of it, just as an example, that's only 29 steps to locate any product in perhaps a search. So how does these large systems, how are they able to have such efficient databases? Well, there's a lot to it, but one of the ways is by using structures like a tree. So when you need to go and look up an item in a database, having this tree structure allows you access to anything in log n because that's the height of the tree. We'll talk about that more as we further analyze some of these algorithms, but this is the basic idea. And so the other thing, and we'll be talking about that this next time, is that there's a lot of different kinds of trees. So it's a huge area in CS, so we're only going to highlight even a couple of them, and then we'll only go deep into a couple of them as well. So the basic idea of this video is to just get your mind wrapped around the data structure in general, which is a node that connects in one direction to another group of nodes, which then each of those repeat that same process. And then to kind of think a little bit about the terminology as well as what they're useful for. So trees are really, really great for storing data. Okay, so that is it for this video. Thank you so much.